In this video, we're going to be implementing k-means in R on the dairy purchase dataset. So the first thing is to get that dataset up and running, and I will explain what it is once we have it in our workspace. Data dairy purchase, just like this. Okay, so when we run this and we take a look, so inside dairy purchase is a collection of responses from farmers. So this is a real data set donated by an agricultural consultant who was working for a company, a client, who was considering launching a new product to, in this particular case, it was to detect a disease called mastitis earlier than existing methodology. So mastitis is an inflammation of the udder of a cow that renders the milk unusable. And it's a very common condition. It's painful for the animal, and it corrupts the milk so it can't be sold. And milk is mixed. So if one cow has mastitis and you find this out later, then you may ruin a whole bunch of milk in the process, and it takes longer for the animal to get better, and there's a bigger risk for complications. And so the questions were, okay, how likely are you to purchase this product once they were told about it? How likely were you to purchase this product, or are you to purchase this product if you had a money-back guarantee? How likely are you to purchase the product if we give you a free trial? And how likely are you to purchase the product if there's a lease option, like you can rent to own, essentially, or lease before you buy or something like this? So these are on a scale like a star scale, 1, 2, 4, or 5. Okay. So let's actually want to know, is it 4 or 5 is the max? 5, okay, so it's perfect. It's just Likert, scale 1 to 5. All right, great. So the first thing we need to do here, and in fact, let's do it both ways. So we're not going to pre-process the data set first. We won't standardize the scores, and then we will standardize the scores just to compare and contrast the two. It's easier to interpret the clusters if you don't standardize. In this case, it's not strictly necessary, because all the variables are on the same scale. They're all 1 to 5, and so you don't have to. But let's kind of table that. So pre-process or not. Okay, so the next thing we want to do is construct k-means. So we'll say k-mean, or model equals k-means df, and then you have to give the value of k. And so let's say 4. Why not? And we'll come back and find the right value of k. So we run this thing, and we'll say model $centers. These are our cluster centers. I'm going to try to run it so that they're all on the same line. Let's see if we can. I really can't do it. The font's too big. Okay, so this is cluster 1, cluster 2, cluster 3, cluster 4. This is the average of inside that cluster. So for instance, in cluster, let's do cluster 3 first. And notice that your cluster 3 may not be the same as my cluster 3. But so for my cluster 3, these people are universally positive. They have 4 stars across the board. 4 stars for question 27, 28, 29, and 30. They are just so positive. It just doesn't even matter what you do, whether you money back guarantee or lease or whatever. They're going to buy this product regardless. The natural counterpoint then is cluster 4. Cluster 4 doesn't really like the product to begin with, but then if you add any additional thing on this, like a money back guarantee or a lease option, their opinion actually goes down. And then the other two, you might think that's kind of a strange observation, but in fact it's true about the other two as well. So we go from 4 stars in group 1, it's just likelihood of purchase, to 3.4, to 2.8, to 3.2. And then a similar thing, although less pronounced, for cluster 2. So in all of these cases, except for the universally positive cluster, it's actually the farmers are more likely to purchase the product than they are to purchase the product with a money-back guarantee. This is one of the great things about cluster analysis. Is you might ask, why is it useful if there's no target to predict? Here, we're seeing one of those pieces of utility, or one of those pieces of value add, in the sense that we are surprised by what the clusters turn up. In this particular case, the cluster is telling us that our customers are not, and across a bunch of different groups that think of our product in a very different way, all of these customers are saying that they are more likely to just buy the product than they are to buy it with a money-back guarantee. This was so surprising that if the same consultant did a follow-up study, or was paid to do a follow-up study for why this is, And the farmers basically said that if you have to give a money back guarantee for your product, then your product isn't worth anything to begin with. Your product either works or it doesn't. And if if I have to lease it first to know that I like it, or if I have to have a trial period, then it's just a bad product. I don't want it. I'm either going to buy it or I'm not going to buy it, and that's it. Amazing. The other thing you can get here is if we say model $ sizes, or I'm sorry, just size, these are the relative sizes of all the groups. And so you can see that while group 3 is the most positive, all above 4 stars across all of our categories, they're also one of the smallest with only 27 people. The largest group by far is the not so positive group, the very negative group. And it turns out that one of the other things that this consultant found was that the size of the dairy, the size, like the number of cows that a farmer had, determined whether, to a large extent, whether they would even consider the product. Because for smaller farms, this piece of equipment is just too expensive. And so most of these 94 here are just smaller farmers. So those are the two things we typically care about, model $ centers and model $ size, to kind of get an idea of what's going on here. Now, I said pre-process or not, and what I mean by that is we could pre-process here, and let's say library caret, and then we say standardizer equals pre-process. Pre-process is a pre-processing step. You feed in the data frame, and then the method you want to use to pre-process. Here we want to use center and scale. And what that means is center it so that the mean is now 0, and scale it so that the 1 unit plus or minus is 1 standard deviation above the mean or 1 standard deviation below the mean. In other words, this is turn into z-scores. You're converting every column into z-scores or t-scores rather than the raw data. So to do this then, we just say df equals predict, standardizer, df. So standardizer is its own, like a model, just like any other model, and we can just use the predict command. And I didn't run that line. And notice, I'll look at the summary of the df now, all of these columns now have mean 0. They've all been centered, and if I were to look at the standard deviation of each one of these columns, like I forget what it is. Is it standard like that? I always forget an R. Oh, duh. Just look at the variance. df $, that one, 1. So the variance is 1, so the standard deviation is 1 for that column. Exactly. The only problem now is if I run this model again with 4 columns and I now look at the centers, the only thing to notice then is that these are in z-scores. So it is harder to interpret in absolute terms. It's impossible to interpret in absolute terms. Not impossible, harder. I'll go back to my original frame. But it's still informative. For instance, I can still tell that my new cluster 1 is my positive cluster because they're 1.5 standard deviations above the mean for basically every single question. Group 2 now is my negative group because they're about 1 standard deviation below the mean for all questions. Group 4 looks much more kind of equivocal because they're about equal to the mean across every question. And then group 3 is slightly negative except for the purchase with the lease, which they're pretty bullish about. So this standardizer, it does impact the clusters. You will get different clusters for sure if you standardize versus not. But then the other thing you're going to have to do is adjust the way you interpret the outputs. The last thing I wanted to talk about is this bit here, and how do we actually pick K? To do this, we're going to need Babson Analytics, and we get that with our source command. I'm just going to copy paste this file path here to speed things up. BabsonAnalytics.r. You know where yours is located. I'm going to run this thing. And the one we want here is elbow chart. So elbow chart, df. If we run this thing, let's move it over here. This is that average within group sum of squares and the number of clusters. That should cluster size, meaning it's like how many clusters do we actually have. So notice this is what I was talking about in a previous video. See how there's a little noise here? There's a little bit shaking. It's not like it's perfectly clear, except that overall, if you kind of like squint your eye or go a little cross-eyed, all that kind of smooths out. And you can just see that we have a huge drop when we go from 2 to 3 clusters, a pretty big drop when we go from 3 to 4. And then by the time we go from 4 to 5, and especially 5 to 6, these improvements in sum of squares, the improvements in densification, compactification of these clusters is really starting to diminish. So if I were in this case, I would pick 4. That's kind of how I would identify things. You will get different EBLO charts, whether if you standardize or not. So you have to be careful with that too. But these are our overall pieces. And I'm sorry to, I thought about whether I go at this video like straightforwardly or build on itself, but I do kind of want to, I decided on the build on itself. You can get k-means up and running like in 2 lines of code. You load and you build the model. There's no problem with that. But we can go back and refine things. We can pre-process to kind of improve our cluster quality, and we can build an elbow chart to find that best value of k. The other thing you might have to do here is go through and remove outliers that can be pulling your cluster centers away, but more on that in a separate discussion.